In this video, we are going to consider another example related to substitution and the area between curves. That is from exercise 5.6, and the question number is 54. So the question is, we need to find the area enclosed by the intersection of the curves, which is given by x minus y squared. That's equal to 0. And our second curve or graph is x plus 2y squared is equal to 3. Again, number one, actually, first we need to find the intersection points. Now, if I just expressed here x and x's in this equation explicitly, let's say this solution, the first one will be x is equal to y squared, and the second one is x is equal to minus 2y squared plus 3. So to find the intersection points, we have to solve this equation. Here we have y squared is equal to minus 2y squared plus 3. Or y squared, actually, if you move everything to the left-hand side, y squared plus 2y squared, that is 3y squared minus 3, that's equal to 0. Or if you divide both sides by 3, here we have y squared minus 1, that's equal to 0. Now we can factorize this, right? Y minus 1 times y plus 1. So we will get 2 roots y is equal to negative 1, or y is equal to 1. So at these points, actually, these graphs intersect each other. See here, actually, both are quadratic functions, right, in y. So suppose that is our... let me just redraw this. Okay. All right. The first one is x equals y squared. So that is our x-axis, and this one is y-axis, right? So x squared, x equals y squared, it is a parabola, something like this. And how about the second one? Its maximum value is 3. Suppose that this one is 1 and 2 and 3, starting from here, right? It actually looks downward. So its graph will be something like this. Okay, the graph is something like this. Okay, so here they intersect each other. They intersect each other. And okay, so let me write here. So that is negative 1. And this point is, it is 1. So we are talking about this region, right? So we are talking about this region, intersection part. Okay, we have to find the area of this region. Okay, so now to do this one again, how do I know this? I should subtract what function from what function. Again, if you draw a vertical line that's parallel to the x-axis here, a vertical line here, it enters the region here and exits the region here, right? And suppose that actually here this point is y1 and this point is y2. At the time, the height of the rectangle will be, what will be the height? Let's say that height will be y1 minus y2. Okay, and we know this function. This function is actually x is equal to y squared. And how about this function? That is x equals negative y2 squared plus 3. So now let me just write our what is this? Our integral here. Okay. So now we're going to find the area. That area is equal to a. So integral, right? Our x is running from negative 1 to 1. So that is negative 1 to 1. And so above, we have this function that is y squared minus, below, we have this function that is minus 2y squared plus 3. So dy, because I'm sure that now here height is positive. So I'm sure that actually our integral will be, what is it, positive, equals integral from negative 1 to 1, y squared minus minus is plus. So here we have 3y squared plus 3 dy. And see here we are integrating this function about the symmetric interval, right? Our interval is symmetric about the y-axis. And at the same time, our function is even function. So by using that symmetry theorem, and also 3 is common factor here too, because of the symmetry, and 3 is a common factor. Our integral takes simpler form, that is from 0 to 1. So here we have y squared plus 1 dy, which is equal to, here we have 6. So 1 over 3, 1 cubed minus y plus y. And integration limits from 0 to 1. So when it is 0 is equal to 0, when it is 1, here we have 1 over 3 plus 1, which is equal to 4 over 3. 6 times 4 over 3, so that's equal to 8. So the area of the shaded region, which is bounded by these two curves, is equal to 8 units squared.